Okay, so let's continue with our discussion on algebraic geometry. So so let me recall what we have seen until the last time. So broadly, algebraic geometry is a study of the geometry of the set of common zeros of a bunch of polynomials. So what we do is we take K to be an algebraically closed field, and of course what is the significance of this is, well, the significance is that you have the Nullstellensatz, which tells you that zeros of common zeros of a bunch of polynomials, the set of common zeros of a bunch of polynomials is not going to be an empty set, provided the set of that bunch of polynomials doesn't generate the whole ring. Okay, so that's the reason why you choose an algebraically closed field. And what we have is basically we have this there is a dictionary, or we rather try to set up a dictionary on one side, which is the geometric side, on the other side being the commutative algebra side. So what we have on the geometric side is the affine space over K, which is actually Kn, namely K cross K cross K, n copies. This is the Cartesian product of K taken with itself n times. Of course n is greater than or equal to 1, and it is Kn, not just Kn, but it is with the so called Zariski topology. So, well, if you just look at Kn, you would normally think of it as n dimensional vector space over K. Okay, but the point is and in a vector space 0 is a very special vector. Okay, but we don't want to think of it as a vector space, we want to think of it as affine space. So 0 doesn't have, the point 0 doesn't have any special meaning. In the case of vectors it does have a special meaning, because a vector always needs an initial point and a terminal point, and we always take the initial point to be the origin. Okay, but here in affine space any two points are literally the same, except that only the coordinates have changed. Okay, so but more importantly, what we have is not just a set, it's not just the Cartesian product. This Cartesian product it consists of n tuples of elements of K. Okay, it's not just the Cartesian product as I said, but there is a so called, what is that Zariski topology? It rather comes from the commutative algebra side. So let me put that on this side. This is the commutative algebra side. On this side we have the polynomial ring in n variables over K. So x1 through xn are n indeterminates or n variables, and of course this is the polynomial ring in n variables. Okay, so these are polynomials in these n variables with coefficients coming from the field K. Okay, and how do you get the Zariski topology? You get the Zariski topology by prescribing, of course any topology is given by either prescribing a collection of closed sets or a collection of open sets, and these two are complementary to each other because a closed set is a complement of an open set and vice versa. So the approach to the Zariski topology is by specifying a collection of closed sets. And how do you specify this collection of closed sets? What you do is, well, you take any subset of this polynomial ring, which means you are just taking a bunch of polynomials in n variables with k coefficients, and what you do is associate to that subset the set of zeros of the set of common zeros of that subset. So this subset here will be all those n tuples which satisfy each and every polynomial in this collection, in this subset. Okay, and we declare sets like this to be the closed sets. So they are given a name, they are called algebraic sets because they are the common zero locus of a bunch of algebraic equations. Okay, the solutions to a bunch of algebraic equations. You can think of the equation corresponding to each polynomial as a polynomial being equated to 0, and then the solutions are nothing but the zeros of the polynomial. Okay, so the algebraic sets are sets like this, and they are if you declare them as closed sets, then you see that they satisfy the axioms for closed sets, and therefore these sets of subsets of this kind taken as closed sets does define a topology on the set Kn, and along with this topology we call Kn as the affine space, n dimensional affine space over K. We give this special symbol and we call this topology Zariski topology. Okay, in honor of Oskar Zariski, whom you could say is a founding father of algebraic geometry from the viewpoint of commutative algebra. Okay, so and then I told you that so there was a so on this side we have a collection of nice sets, namely the algebraic sets, which are the closed sets, but on this side you seem to only have subsets of the polynomial ring, but then a subset doesn't make sense as a sub object of the polynomial ring, and the right sub objects are ideals. Okay, and of course everything here is commutative. The K is of course always a commutative field. We are in this course we are only worried about commutative rings. So and therefore ideals are always two-sided. Okay, so the point is if you want the right objects on this side, more interesting than the subsets are the ideals. And how do you pass from subset to an ideal? This is a very general yoga, it is a general philosophy that you can always take the smallest sub object which contains your subset. In any mathematical structure, if you have a subset which is not a sub object, then how do you get a sub object? You just look at the smallest sub object which contains that subset. It is called the sub object generated by the subset. Okay, so in this case you can take the ideal, the sub objects which you are interested in are ideals. Of course you can think of subrings also as sub objects. Okay, but subrings are not going to help, because the point is the moment this set contains a unit, then the zero set will become empty. Okay, because a unit has to be just a constant polynomial which is non-zero. Okay, and that constant polynomial is never going to vanish anywhere, so the zero set will become empty. So certainly you are not interested in sets like this which contain one or which can generate one. So basically you are only interested in, so that tells you that you are not interested in subrings. And what other objects, sub objects can you think of? You can think of ideals. And why ideals? Because ideals are really nice sub objects, because the nice sub objects are the ones which can give you quotient objects. Okay, so if you have ring and you have an ideal, then you can get the quotient ring, okay, whereas of course if you have a ring and a subring, I am not going to get any quotient, okay. So from the point of view of a sub object being the right one, if it gives a decent quotient object, you see that ideals are preferred, okay, ideals are the right choice and subrings are not. But anyway we do not want subrings because this is going to end up as the null set if you are going to take a subring, okay. So the upshot of all this is that you look at the ideal generated by this subset, which I put as bracket S, and then you see that if you take the 0 set of the ideal generated by S, okay, that turns out to be the same as the 0 set generated by S. I mean the 0 set of S. The 0 set of the ideal generated by S is the same as the 0 set of S. So what it tells you is that if you replace a set by the ideal it generates, you are not going to change anything here, okay. So the advantage of all this is on this side you have closed subsets, on this side you have ideals, okay, and not just subsets. And what is a prescription? Though we started out with subsets, we always take the ideal generated by the subset and work with that, okay, and that does not change anything on this side, okay, because of this equality. Now so as I told you, the whole purpose of algebraic geometry is to look at this these two sides of the picture, okay, and go from one side to the other and keep translating what properties on one side mean on the other side. So geometric properties on this side should mean they should give rise to some ring theoretic properties, which means they will give rise to some ideal theoretic properties. More generally they might give rise to module theoretic properties on this side, and conversely some module theoretic or ideal theoretic properties or ring theoretic properties on this side will correspond to geometric properties on this side, and the aim of algebraic geometry is to discover this relationship, okay. So the first thing I wanted to say is well, but there are 2 points I have to mention. So the first point is, so let me again recall, an algebraically closed field is a field in which if you take a polynomial of one variable in one variable over that field, and if it is non-constant, then all its zeros are there in that field, okay. So normally field theory tells you that if you have a polynomial over a field, then you may have to go to an extension field to find the zeros of the polynomial, okay. And in fact field theory gives you what is called as a splitting field for a given polynomial, which is a kind of a smallest field extension over which the polynomial completely splits into linear factors. But you do not have to worry about such things, I mean if you are working with an algebraically closed field, because the definition of algebraically closed field tells you that if you have a polynomial it will already split into linear factors. That means which is equivalent to saying that all the zeros of the polynomial are already elements of this field, okay. But the story does not end there. The important thing is when you define algebraically closed field, it is only for one variable, okay. But when we do algebraic geometry in this general sense, we are worried about polynomials not in just one variable, we are worried about polynomials in several variables. And then the question that arises is, if you give me a subset of polynomials, or for that matter the ideal that it generates, and look at the 0 set, what is the condition that the 0 set is non-empty, okay. And the Hilbert Nullstellensatz tells you that this will be non-empty so long as this ideal is really a proper ideal, so long as this ideal is not the whole ring or the unit ideal, okay. So in other words this should not contain a unit. We all know that if it contains a unit, if S contains a unit, it is very clear that this is empty, okay. And the Hilbert Nullstellensatz tells you that is the only case when it is empty. So long as this does not contain a unit, and of course it is very important that well, I should correct my statement a little, this may not contain a unit but this might generate a unit, okay. So to be very strict, this ideal should not contain a unit, which is the same as saying this ideal should not be the whole ring, okay. in that case, and then and only then will the 0 set be non-empty, okay, and that assurance is given to you by the Hilbert-Nullstellan sets, okay. That is one important thing. Then the other thing is the other important theorem that comes is the Hilbert's basis theorem or Emmy-Noether theorem, okay. So you see, you already see the impact of results on this side, which means something on this side. You see, the fact that the Hilbert's Nullstellan sets is basically a result which comes from this side of the diagram, okay. If you want to think of commutative algebra also as involving field theory for that matter, because you know fields come because you know you start with a ring, basically you start with rings which are integral domains, and then if you go to the quotient field or the field of fractions, then you know studying things over that already leads you into field theory, okay. And so you know Nullstellan sets is a kind of result that you know comes in on this side of the picture, but geometrically it means that you know the 0 set you are working with gives you conditions when the 0 set you are working with is not empty, okay. That's already a that's already a translation from a result on this side to this side, okay. And but the way I have given it, I have already given it on this side, okay. I haven't told you the commutative algebraic version of the Nullstellan sets, which I will do, okay. And the other statement that I am worried about is that I want to talk about is about the Hilbert basis theorem or the Emmy-Noether theorem. What does it say? It says, well, it says that if you start with a ring R, a commutative ring, of course you know you must always remember that we always work only with commutative rings with 1, and we always assume that all ring homomorphisms take 1 to 1, okay. So if you start with a Noetherian commutative ring, okay, which means that the ring satisfies the property that every ideal is finitely generated, then if you take a polynomial ring in finitely many variables over that ring, the polynomial ring also becomes Noetherian, okay. So if you take for the ring a field, you know a field is always Noetherian because it has only 2 ideals, namely the 0 ideal and the full field which is the unit ideal, so it is Noetherian. And now if you apply Hilbert's basis theorem or Emmy-Noether's theorem, you get that this ring is Noetherian. What it means is therefore that every ideal is finitely generated, okay. Now what is the importance of saying that an ideal is finitely generated? The importance is that every element in this ideal can be written as a finite linear combination of a fixed number of elements with ring coefficients, that is what it means. But what it really means is that you can take for this generating set only a finite set of polynomials, and what it means therefore is even though you start with a set which is probably infinite, okay, or you start with an ideal which is infinite, okay, in fact an ideal will be infinite because even if it has one element then it will contain all multiples of that element by the ring elements, and there are infinitely many elements here because K is any algebraically closed field is infinite, that is a result from field theory, okay, and this polynomial ring is also infinite. So all these ideals are all going to have infinitely many elements, and when you look at the common zeros of elements in the ideal, you seem to be looking for common zeros for infinitely many polynomials. But then what the Hilbert's basis theorem tells you is that that is not what is happening really. What is really happening is you are just looking at the 0 set of finitely many polynomials. So what it tells you is that even if S is infinite, in any case any ideal like this will always be infinite. That ideal is the same as the ideal generated by finitely many polynomials, okay, and therefore the 0 set is just the common zeros of these finitely many polynomials, and in fact this is a set this is the same as the intersection of the 0 sets of the individual polynomials, okay. Z of Fi is just the zeros of Fi, okay, and then if you take the intersection you will get the points which are zeros of all the Fi's, which is exactly what this means. This is the set of common zeros of all the Fi's, and of course this tells you that you are always only going to solve finitely many equations, okay. And why this is important is it's also important for computation, okay, because once you have finitely many things to deal with, you can have inductive procedures based on some ordering. For example, you can do a lot of computations in commutative algebra using software, and all this is possible just because of this result, that you are only dealing with finitely many polynomials at a time, okay. So that is the importance of these two very basic but very important theorems. One is the Hilbert-Nullstellensatz and the other is the Hilbert-Basius theorem, okay. Fine, so that's the setup now. So what I want to do is I want to give you something that goes in both directions, okay. So already I have this Z which associates to every subset or every ideal on this side the common zero locus on this side, okay. I also want to give something on this in this direction, okay. I want to give something in this direction. So so when I go from this direction, so from how do I go from here to there? So you know, if so let T be a subset of An, okay, and mind you this is just a subset, it's just some collection of points, okay. I am not requiring that it is closed or open or something like that, I am just taking any subset, and what I do is from here I associate to T I of T, which is called the ideal of T, okay. This is the ideal of T, okay. And what is the ideal of T? This is a set of all polynomials in the polynomial ring such that f of okay, so let me write it like this: f of t equal to 0 for every t in capital T, okay. This is called the ideal of a subset, okay. So there are two statements I want you to understand. First thing is I am defining a set and I am calling it an ideal, okay. In general that is not correct. I can define a set, then I have to verify it is an ideal, okay. So the fact is that, but if you really look at this definition, it is obvious that it is an ideal, because you see if you take two such f's, say f1 and f2, then if f1 and f2 both vanish at every point of t, then so does the sum, okay. And of course 0 vanishes at every point of t, so 0 is there, so this closed under addition this has 0, and of course for that matter if f vanishes at every point of t, so does minus f, okay. And also if f vanishes at every point of capital T, then multiplying f by a g will also vanish at every point of capital T, so this is an ideal. So it is in fact an ideal, and this is called the ideal corresponding to the subset, okay. And so you see now we have so basically what is happening is that to a subset here we associate a set here which is actually closed, okay, it is an algebraic set, and in fact for an ideal here also we can associate a subset here which is actually closed, okay. And in this direction given a subset you associate an ideal, okay. So you can see more or less that on this side you are worried about closed sets, okay, and on this side you are worried about ideals, okay. So let us explore the properties of these two associations. Many of them are quite quite straightforward. So the first thing is so let us look at the association in this direction, okay, that associates to every subset the zero set of that subset. So the the fact I want to put is that this association is actually inclusion reversing. Okay, on this, see, on both sides you have subsets. Only thing is here the special subsets that we are interested in are closed subsets, and here the subsets that we are interested in are ideals. Okay, but nevertheless inclusion makes sense on both sides as a partial order. Okay, and what I want to say is that both of these associations, they just invert they are not order preserving, but they are order reversing. Okay, so what it means is that, you know, if S1, so let me write that down as a lemma. It's pretty easy to see. If S1 is a subset of S2, then, well, Z of S1 contains Z of S2. The second thing is the corresponding result on this side. If T1 is contained in T2, then ideal of T2 contains ideal of T1. Okay, so it's if you look at it, it's pretty easy to understand. You see, if you start with S1 inside S2, probably I'm making a mistake somewhere. Okay, I'm making some obvious mistake. So let me talk through this. Okay, so you see, S1 S2 has more equations than S1. Okay, so a solution, a point of the affine space which satisfies every equation in S2 will always satisfy every equation in S1. So this is correct, right? I think there isn't anything wrong there. And look at this, if T1 contains T2, okay, then if you take a function which vanishes at every point of T2, then it will vanish at every point of T1, therefore probably this has to be the other way around. Okay, so probably that was a mistake you were pointing out. Yeah, so if T1 is contained in T2, then the ideal of T2 is contained in ideal of T1, because the way I first wrote it, it seems to be order preserving, which is not correct. Okay, fine. So this is quite obvious, but what is not directly obvious is the following thing. You see, what happens if you go and come back? Okay, so if I start with the T on this side, okay, then I take the ideal of that, and then I take the 0 of that, what do I get? So this is something that one has to worry about. And then the other one is the other way around. If I start with well, I said a subset here, I take the 0 set of that, then I take the ideal of that, what do I get? Okay, so this is what we want to investigate, and the answer to that is, well, the answer to this is that you get the closure of T. Okay, mind you, I start with the set T. The set T need not be closed, but when I take I of T, it becomes an ideal, and when I take Z of I of T, it's a closed set, because Z of anything is closed by definition. Therefore what I am going to get is a closed set which contains T. T is of course going to be here, but it's very clear, any point of capital T will be a common 0 of all the functions which vanish on all of T, and therefore it's going to be here. So it's clear that this contains T, and it's a closed set containing T, but the fact is that it is the smallest closed set which contains T, and therefore it is T closure. Okay, and then as this is concerned, this is literally the involves the commutative algebra version of the Nullstellar ansatz. So what it says is that this is just the radical of the ideal generated by S. Okay, and so the so as for the proof, I think 1 and 2 are obvious. Okay, they are quite straightforward. Okay. The question is with 3 and 4, alright. So if you look at 3, so let us prove 3. Clearly T is contained in Z of I of t, right, that is very clear, because every point of t is a common 0 of all those functions which vanish at every point of t, that is what it says. I of t is all those functions which vanish at every point of capital T, and Z of I of t is all those points at which all these functions vanish, okay, and therefore T contained in Z of I of t is obvious. But more importantly, if T is contained in F and F is closed, okay, then what will happen is that you will see that it will follow that Z of I of t is contained in F, okay. What this means is that Z of I of t, because Z of I of t is already closed, it means that Z of I of t is the smallest closed set which contains T, it is a closed set which contains T, and Z of I of t is a closed set which contains T, and whenever some other closed set contains T, that closed set also contains Z of I of t. So this implies that Z of I of t is equal to T bar, because by definition the closure of a subset is the smallest closed set which contains that subset, and which you can obtain set theoretically as the intersection of all the closed sets which contain that subset, okay. So I think so I have written it will follow that, it is something that you can very easily check, okay. And as for the proof of 4, well, so one way is kind of obvious, and it is the other way which is not obvious and which involves inverse transits, okay. So you can see that I of Z of S is the same as I of Z of ideal generated by S, because Z of S and Z of ideal generated by S are the same, okay. And I think it should be very clear that this contains radical of S. This should be very clear, because you see, what is an element of the radical of S? Radical of the ideal generated by S. It means it is an element whose power is in the ideal generated by S, okay, and that, but any element in the ideal generated by S will be in this ideal, okay, and therefore it will be essentially an element that will vanish at every point of Z of S, okay, and therefore the element whose you started with will also vanish at the points of Z of S. So this will be obvious, okay. What is more difficult is the other way around, namely, if you start with a function which vanishes at every point of Z of S, then some power of the function is actually in the ideal generated by S. That is the non-trivial part, and that is precisely the commutative algebra version of the Hilbert-Nullstellan sets, okay. So let me write that. This is obvious, since F belongs to root of, I mean ideal of radical of the ideal generated by S means F power R belongs to F power M belongs to ideal generated by S. This implies which implies that f power m belongs to I of z of s, okay, and so in fact I should say more importantly, not only this, what it means is that f power m belongs to, okay, so f power m vanishes on z of s, okay, which means f vanishes on z of s, okay. So this means that I mean this means that if you start with an f in the radical of the ideal generated by S, it has to be in the ideal of z of s, okay. So this is kind of obvious. What is not obvious is the following. Conversely, if f is in I of z of s, that is f vanishes on z of s, then f power m belongs to S for, so let me add, for some m greater than 0 due to the commutative algebraic version of the Hilbert-Smith cells, okay. So so what is the commutative algebraic version? Let me expand on that. So here is Hilbert's Millstone sets. So this is what is called the strong form commutative algebraic. If K is an algebraically closed field, and I in K x1 etc. xn is a proper ideal, okay, then the ideal of z of I is contained in rad I. This is the commutative algebraic version. In fact, we often say it as I of z of I equal to rad I, okay, but the fact that I of z of I contains rad I is something that is obvious, okay, but what is not obvious is that I of z of I is contained in rad I. Namely, if there is a function which vanishes on z of I, then some power of the function is in I, because radical of an ideal is just all those elements, some power of which, some positive integral power of which is in the ideal, and you can check that that's a bigger ideal in fact, okay. And what this says is that if a function vanishes on the 0 locus of an ideal, then some power of the function has to be in the ideal, which means that function has to be in the, it may not be in the ideal, but some power is in the ideal, therefore the function is in the radical of the ideal, okay. So you should think of the radical as trying to expand the ideal by trying to take all possible nth roots of elements in the ideal, okay. So this is the Hilbert-Knudsen sets, this is the commutative algebraic form, okay. Oh yeah, so as one of the students rightly points out, maybe okay, so let me make the correction right from here. Let me call this, let me use a script I, okay, for going from this direction to this direction. So I'll change this to script I, okay, so that things become far better. So this changes to script I, this changes to script I, and this changes to script I. So does this. Yeah, so it's a lot more helpful to have this kind of notation which doesn't confuse. So I'll change it everywhere. Yeah, of course the statement here that f power m is in the ideal generated by S for some m greater than 0 is another way of saying that f is in the radical of the ideal generated by S, which is what we want for the other inclusion, okay. And here let me put script I here so that it becomes better to read, okay. And you see I gave a so called weak form of the Hilbert-Knudsen sets, okay. What was the weak form? The weak form was the assurance that so long as an ideal is not the unit ideal, the 0 set defined by the ideal is going to be non-empty, okay. And that weak form can be deduced from this strong form as follows: if an ideal is not the unit ideal, then that translates to the fact that the radical of the ideal is not also a unit ideal, okay. An ideal is you can check that the ideal is a unit ideal, an ideal is a unit ideal, namely the whole ring, if and only if the radical of the ideal is also a unit ideal. The reason is because of the fact that if a power of an element is a unit, then that element itself has to be a unit, okay. So I not being the unit ideal, I being the unit ideal is the same as the radical of I being the unit ideal, okay. And then of course you see if Z of I is empty, okay, if Z of I is empty, then the ideal of the empty set is a whole ring, okay. So if you assume that I is not a unit ideal, then you will get a contradiction from this if Z of I is empty. So you should read it, in fact you should read it with equality, okay, because the other inclusion is obvious. So this strong form of the Hilbert-Knudsen sets does ensure that so long as I is not the unit ideal, the 0 set is non-empty, okay. So that is how the strong form gives the so called weak form, okay. So what one needs to know is, since you have two associations going in two directions, you would like to make this you would like to see this as a bijective equivalence, and it is obvious that you will have to restrict the subsets here and the subsets there. And what we are going to do next is to go towards that, okay. So the see, the problem is on both sides the arrows are not injected, the associations are not injected. For example, if I take an ideal I and if I take the radical of the ideal I, they both go to the same thing here, okay. So if I take I here, which is contained in its radical, every ideal is of course contained in its radical, okay, then both of these things they go to the same thing, the 0 sets are the same, the 0 sets are the same, okay. So you have two different things going to the same thing here, okay. So to avoid this, what you will expect is that on this side you should replace ideals by radical ideals, okay, not just look at all ideals. First of all, not look at all subsets, you pass from subsets to ideals, and then don't just look at ideals, look at radical ideals, okay. Then you see that you can expect that this kind of a thing does not happen, okay. So on this side you put radical ideals, right, and on this side you put closed sets, then it is a fact that this is it's a bijective correspondence. So radical ideals on this side and closed subsets on this side is the first layer of the bijective correspondence, okay. And the other important thing is, you know, this statement about inclusions being reversed, what it tells you is that as the ideals become bigger, the zero sets become smaller, okay. So in fact when I say ideals become bigger, it is with respect to inclusion, and you know the biggest ideals with respect to the inclusion, non-trivial ideals with respect to the inclusion, are the maximal ideals. So what you can imagine is that the biggest ones on this side are the maximal ideals, and they will correspond to the smallest sets on this side, and what do you expect them to be? They will be points, okay. So what will happen is that the biggest ideals here, the maximal ideals, they correspond to the smallest sets here, which are the points, and it's again a corollary of the Hilbert-Nullstellan sets and all this machinery that we have built up, that the set of points in the affine space can be simply identified with the set of maximal ideals in this commutative ring, okay. And the beautiful thing is, so therefore you know you are able to see the set of points here, which is geometric, as again a set of points there, but these are not actually points here. You have to form another space called the maximal spectrum. The maximal spectrum of ring is a set which contains all the maximal ideals of the ring, and the fact is, if you take the maximal spectrum of this polynomial ring, what you get back is a affine space, okay. But this is getting it back as a set. The truth is it does not stop there. The truth is that on this maximal spectrum here there is a Zariski topology, and if you take that Zariski topology and give that topological structure to the maximal spectrum, then that topological space becomes homeomorphic to this. So it is not just a bijective correspondence, but it is a topological homeomorphism. So you see, in conclusion what is happening is that you have finally managed to completely rub off the geometric side and obtain it completely using commutative algebra. So you see, your affine space along with the Zariski topology can be completely forgotten, and you can recover it only from the commutative algebra side by doing what? By taking the so called maximal spectrum of this commutative ring, which means take the set of all its maximal ideals, and on that maximal spectrum impose the so called Zariski topology. There is a Zariski topology on this side, there is something called a Zariski topology on any ring, on any commutative ring, which you would have come across in a course in commutative algebra, but anyway I will recall it. And the fact is, if you put that topology on this, on the maximal spectrum, amazingly you get back your affine space. So the beauty, you see, the beauty of the dictionary is that I am able to see the affine space on this side without ever going to that side. So you see, this is the kind of translation that one is able to do, and then there are many more things that happen on this side that can be seen here, and vice versa, okay. So this discussion will proceed in that direction, okay. So I will continue in the next lecture.